What's up, ladies and gentlemen? Today we're going to focus on the body basics. Let's get it popping. So, musculoskeletal system is an important system in the human body. It is made up of four different types of tissues. Number one are bones. Bones are highlighted here in this diagram, and they are light but strong structure that provides leverage, support, and protection to the organs of the body, as well as leverage points for muscles to pull on. In total, there are 206 bones in the human body. Now, where these bones come together those are called joints, essentially where two bones touch. And there's several different categories of joints depending on how movable those joints are. So, for example, some bones that come together don't move a lot at all. Okay, so they're very rigid in nature. Versus other places where bones come together, they are more freely movable. Okay, so how movable they are is determined by several different things that we're not going to focus on here in this PowerPoint. But just to understand here, there are several different types and classifications of joints depending on how movable they are. Muscles are the third point of musculoskeletal system, and we'll focus on it predominantly in this PowerPoint slide set. And then we got tendons. Okay? Essentially, tendons are the tissues that connect muscles to bones. So when muscles contract, okay, they pull on tendons, and tendons themselves, they will pull on the bones. Think about tendons kind of like ropes that are very elastic in nature. So with muscles they are a combination of muscle tissue, connective tissue, nerves, and blood vessels. And kind of like in Shrek there, where Shrek talks about how ogres have different layers there, muscles themselves have different layers as well. Okay, so for example, okay, we've got epimysium is connective tissue that connects to paramysium is another layer, and endomysium is another layer. I'm not going to focus on all these small structures here, but just understand here muscles incorporate a variety of different structures there and have several different layers of connective tissue. Now, muscles are a part of the neuromuscular system. Muscular meaning muscle, neuro mean neurological. Okay, and so essentially here, every muscle there is a part of a motor unit. So what a motor unit is a motor neuron. Okay, so a nerve cell there, and all the muscle fibers it innervates. Here's an example picture of that. Okay, we've got our motor neuron there. Okay, comes down there, and these little fingers of the motor neuron there attaches to several different muscle fibers. Okay. Now, the size of this motor unit there can involve only a few fibers for fine movements to a large number of fibers for gross movements. Example of fine movements would be number one, your eyeballs. So your eyeballs, when they move, they got to make small, precise movements. So the motor units that control the eye, there are many different motor units, and each motor unit only attaches to a few different muscle fibers. Okay, so that helps with very fine movements. Another example would this be the motor units that innervate your finger muscles. Your finger muscles have to make very precise movements, so therefore there's several different motor neurons there that connect to your finger muscle fibers, and each motor neuron there only connects to a few different fibers. On the flip side here, movements like walking, okay, you might have one motor unit, okay, that connects to hundreds of different muscle fibers. So for example, okay, in your leg muscles there only might be a few motor units there, but each motor unit connects to hundreds of different muscle fibers. So depending on the precision of the movements needed at that particular body part will determine how many muscle fibers that motor neuron connects to. Now, depending on the movements there, how intense they are, will determine the motor unit activation level. Okay, so let's take these two examples here. Both of these are squatting movements here. Okay. On the left side, we got a person that's squatting with no weight on his back. Okay. On the right side here, we got a person who's squatting who's got a lot of weight on his back. Okay. So if I am only lifting my body weight there, that only requires a small amount of motor unit activation, meaning only a few motor units are actually being used in order to perform a bodyweight squat. However, in a very heavy back squat there's going to be many different motor units that are going to be active in order to lift this very heavy weight. So lighter weights require fewer motor units to be active versus heavier weights require more motor units to be active. Similarly, slower movements, so for example, walking, require fewer motor units to be active versus faster movements like sprinting require many more motor units to be active. Now, with your muscle fibers there are three main muscle fiber types. We've got type 1 muscle fibers. Those are considered to be slow twitch in nature. And then we've got two different type 2 muscle fibers, both of which are considered to be fast twitch. We got type 2A, which are like an intermediate muscle fiber type. And then we got type 2B or type 2X. Reason we've got type 2B or type 2X is that both are kind of the same names for the same type of muscle fibers, but just depending if you're looking at newer research or older research, one might be more readily used than the other. But just understand type 2B or type 2X means the same thing. Let's go over the characteristics of these different muscle fiber types in the next slide. So we've got several different characteristics here in this chart on the left side. And on the top there, we've got slow twitch, type 1, fast twitch A, or type 2A, and fast twitch B, type 2B, or type 2X. So let's look at the difference between these different muscle fiber types. First, let's look at contraction time. So how long does it take for that muscle to contract? For slow twitch muscle fibers, they contract very slowly, versus type 2A is going to be much faster, and type 2B is going to be the fastest. So contraction time is going to be very quick in type 2B, a little bit less quick in type 2A, and relatively slower in type 1. Number 2, size of the motor neuron. So the motor nerve there, that connects to these muscle fibers here, what's the size of it? Very small in type 1, and then on a continuum there to be very large there in type 2B. Resistance to fatigue, so how quickly do these muscle fibers there get tired? What you'll notice here is that type 1 muscle fibers are very resistant to fatigue, meaning that they take a very long time to actually get tired. Versus type 2A, they tire out a little faster. Type 2B tire out very quickly. Which activity primarily uses these muscle fiber types? Aerobic types of activities typically use a greater majority of type 1 muscle fibers, versus type 2B is going to be short-term anaerobic, and then type 2A is going to be long-term anaerobic. So be able to perform pretty intense bouts of activities for a long period of times, versus type 2B is going to be very intense activities for a very short period of times, and type 2A is going to be aerobic activities, that performed over a long period of time. Force production, type 1 produces the lowest amounts of force, versus type 2B is going to produce the highest amounts of force. Mitochondrial density, or how much mitochondria are in these muscle fibers. Lots in type 1 versus very few in type 2B. And this kind of goes along with being resistant to fatigue. So with more mitochondria, meaning the type 1 muscle fibers are very resistant to fatigue, versus low amounts of mitochondria means that type 2B muscle fibers are going to fatigue very quickly. Capillary density also goes along with that resistance to fatigue. So lots of capillaries there in type 1 muscle fibers versus very few in type 2B, with type 2A being kind of in between. So, and the reason why there are more capillaries in type 1 muscle fibers is that they use a lot of oxygen, So the more capillaries there, more oxygen can get to those muscles, and that in turn means that they can rely on aerobic energy systems versus anaerobic energy systems to produce force. Oxidative capacity, again, along the same lines of capillaries and mitochondrial density, highest in type 1, lowest in type 2B. glycolytic capacity, okay, glycolytic kind of referring to glycolysis, or more so referring to anaerobic sources of energy. So if we're focusing on anaerobic sources of energy, type 2b are going to use the most there, okay, type 2a as well, okay, and type 1 is going to use the least. And lastly, but certainly not least, major storage fuel source. So type 1 muscle fibers are going to get a lot of their energy by the breakdown of triglycerides. So triglycerides, kind of a fancy term meaning fats. So type 1 muscle fibers are very useful in breaking down fats. Type 2b, okay, and type 2a, they're going to mainly use glycogen, oftentimes muscle glycogen. Think about glycogen kind of like stored areas of carbohydrates, as well as creatine phosphate. Creatine phosphate is a source of anaerobic fuel. So if I were to try to summarize all these different characteristics, think of type 2b as your biggest muscle fibers, so they can produce the most force, they can contract the fastest, but because they can do those things, they tire out the quickest. Likewise, type 1 there are going to be these smaller muscle fibers, but they utilize oxygen a lot more, so therefore they're very resistant to fatigue. But because they are the smallest, they cannot produce as much force. Type 2A, think about them as kind of being in between type 2B and type 1. But I'd say is if they were going to err on the side of being closer to one or the other, type 2A is probably a little closer to your type 2B muscle fibers than type 1. So I wouldn't say it's directly in the middle there. So for athletes that are very successful in different sports, they typically favor one type of muscle fiber over the other. So for example, marathon runners, they've got to run for long periods of time without fatigue. And therefore, they are going to have a emphasis on having more type 1 muscle fibers there than type 2. And that's because, again, type 1 muscle fibers are very resistant to fatigue and keep going on and on and on for long periods of time. Versus type 2 typically fatigue much faster. Now, on the flip side there, if you look at sprinters and jumpers have to produce a lot of force very quickly at high speeds. So they are going to have more type 2 muscle fibers than type 1. In the middle there would be your average male, okay, that is not doing a whole lot of activity there. So therefore, again, the activity that you're more successful in can oftentimes be determined based on how many type 2 to type 1 muscle fibers that you have. Now, whenever you're performing any activity, there's a specific order in when the muscle fibers are recruited, because your body is lazy and wants to do the minimal amount of work needed to produce the force needed to complete whatever activity you are focused on. Okay? So whenever you start any type of movement, okay, it could be a jump, it could be a run, it could be a swim, it could be cycling. Okay? Type 1 muscle fibers are recruited first every single time. Not type 2, type 1 muscle fibers are recruited first. Because your body wants to use these type 1 muscle fibers because they are the smallest and they are the most fatigue resistant, meaning that you're not going to get tired very easily. So they're going to try to recruit all the type 1 muscle fibers to produce the given movement there. However, as we know, type 1 muscle fibers produce the least amount of force. So if we recruit all the type 1 muscle fibers and we're still not able to produce the given force needed to produce the movement, then we have to move up to the next level of muscle fibers to recruit them. So if type 1 muscle fibers cannot produce enough force, then the type 2A muscle fibers are recruited next. Okay? And we'll try to recruit as many type 2A muscle fibers needed there to produce enough force. Okay? Now, if type 1 and type 2A are not enough to produce enough force, then and only then are your biggest, largest, fastest moving muscle fibers recruited. Those again would be your type 2X muscle fibers. So let's give an example of this. Let's say, for example, you've got a weightlifter and they are squatting 500 pounds. And this is a very heavy weight for the person who's squatting 500 pounds. When the person puts the bar on their back there, okay, and starts to perform reps of squat there, the only muscle fibers that are going to be recruited initially are going to be the type 1 muscle fibers, okay? Because your body, again, wants to do recruit the very fewest amount of muscle fibers to lift the weight. However, this is a very heavy weight, and the type 1 muscle fibers are not able to create enough force to lift that 500 pounds. So as this person's squatting there, type 1's not enough, so then they've got to, in addition to recruiting all those type 1 muscle fibers, the type 2A muscle fiber is going to be recruited next. So that person's squatting, type 1, using all the type 1 and type 2A muscle fibers it can, but that still is not enough to lift the weight. So therefore, this person needs to move on to the last level of muscle fibers and recruit all the type 2X muscle fibers as well. And only by recruiting all the type 2X muscle fibers, along with using the type 2A and type 1 muscle fibers, only that's going to be enough there for that person to squat and lift that heavy weight. So again, the activity needs to require enough force there in order to recruit these type 2A muscle fibers, and especially the type 2X muscle fibers. Let's take a look at selective hypertrophy, okay, and specifically looking at this shot putter there, okay, shot putter by the name of Werner Gunther. Okay, this was a big dude, 6'7", 280 pounds there. And here's a breakdown of his muscle fibers there. So what I want you to notice here is that the percent of his muscle fibers, okay, between type 1 and type 2 are going to be 60% type 1 and 40% type 2. Okay? And that might seem kind of weird because we know shot putters, okay, they have to produce a lot of force very quickly to throw that shot put, okay? But they don't need to perform several different shot puts in a row. They perform one shot put, rest a couple of minutes. Perform another shot put, rest a couple of minutes. So what's interesting here is the type 2 muscle fibers, number of type 2 muscle fibers, is only 40% of the total muscle fibers he has, versus type 1 was 60%. You would think that Werner Gunther there would have more type 2 muscle fibers than type 1. But here's where the difference comes. Because Werner Gunther there performed a lot of heavy movements, okay, try to produce them very quickly there, okay, the activity and training he underwent there used more or really emphasized type 2 muscle fiber use. Okay, so the total area of his type 2 muscle fibers was almost 3 times as great as the type 1 muscle fibers. Okay. So what does this tell us here? What this tells us here is that the percent of muscle fiber breakdown you have is based off of genetics. Meaning that Werner Gunther there can't increase this percentage of type 2 muscle fibers versus type 1. Okay. So he's going to have more type 1 muscle fibers in his body compared to type 2. Any sort of training he does is not going to change that. Okay. However, though, the total area of muscle fibers, okay, can increase based on the type of training that you undergo. And since Werner Gunther there performed a lot of weightlifting movements to get strong, he got very big there, and his movements were very fast and explosive in nature, he recruited his type 2 muscle fibers a ton during training. And since our type 2 muscle fibers tend to be our biggest muscle fibers there, okay, they are the ones that will grow the most if you actually train them. So that's why, even though he had fewer percentage of type 2 muscle fibers, okay, the total area these type 2 muscle fibers took up there in his body was a lot greater than his type 1 muscle fibers. Now, let me make very clear. Every time Werner Gunther throws a shot put or performs any sort of weightlifting movements, does he recruit his type 1 muscle fibers? Absolutely. If we go back to our recruitment muscle fibers example there, every time he performs a weightlifting movement and throws that shot put, the type 1 muscle fibers are definitely recruited first. So he is using his type 1 muscle fibers. But In order to move that shot put quickly, he has to produce force quickly. So the type 1 muscle fibers might not be enough to produce the necessary force fast enough to throw that shot put. And therefore, because of that, in his training, he had to recruit the type 2A and type 2X muscle fibers to perform his weightlifting movements and to perform his shot put throws. Now, when our muscles get bigger, how do they get bigger? And while this is kind of up to debate in the literature out there, okay, there are kind of two different ways that our muscle fibers could possibly get bigger. Okay, number one could be sarcoplasmic hypertrophy, meaning that your muscles get bigger. Okay, but what gets bigger in your muscle fibers are mainly the fluid in your muscle fibers. There's more fluid in there, and the non-contractile components, meaning the parts of the muscles that do not actually create the tension, okay, when your muscle fibers contract. Examples of these might be blood vessels. Examples of these might be the mitochondria there. Okay? In general, okay, it was thought in the past there that bodybuilders typically have more sarcoplasmic hypertrophy, meaning that the size of the muscles increase mainly due to the increase in fluids and the non-contractile components like mitochondria, like blood cells. On the flip side, we've got myofibrillar hypertrophy. Okay, this increases in the muscle size there due to the increase in the contractile tissue within the muscle fibers. Okay. Technically, if you want to get it specific there, the increase in size of the actin and myosin in your muscle fibers. But I'm not going to really focus on those different contractile components in this. Just understand the contractile components is thought in myofibrillar hypertrophy is what get bigger, what causes the increase in muscle size. Okay. And due to this there, okay, it is thought that we see more myofibrillar hypertrophy increase in muscle size due to speed and power type athletes, such as Olympic weightlifting. Again, I'm not going to get into the debate on whether it's true sarcoplasmic muscle size gets bigger due mainly to sarcoplasmic hypertrophy or myofibrillar hypertrophy. Just understand there that our muscles can increase in size due to either the contractile components getting bigger and or the increase in other parts of the muscle taking up more of that muscle cell. So when our muscles are producing force there, okay, we use different energy systems in order to create that force. And the duration of the activity, as well as how much force is needed to successfully complete that activity, will determine which of our three different energy systems we tend to be emphasized in creating that force. So if you see here on this diagram, we've got the power of energy production, meaning essentially, okay, how much force is needed. Towards the bottom would be low force. Towards the top would be high force. Along the x-axis here is the duration of energy production, or how long do I need to produce this force. Three different energy systems there. We've got our alactic energy system, okay? And this is the energy system that is mainly used in the human body for activities that last 10 to 12 seconds or less. Okay? And specifically when these activities require a high amount of force to be produced. Okay? Good examples of activities lasting 10 to 12 seconds might be, or less, might be a 100-meter dash. Okay? Other examples of this might be a vertical jump. Other examples of this might be a slap shot in hockey. Other examples of this, might be sprinting 10 yards and coming back 10 yards. Okay? So short bursts of activity that require a lot of force production there are going to primarily use the alactic energy system. Now, activities that require activities that need to be done over a long period of time, we cannot sustain a high level of force production for that long period of time. Okay? So These activities, okay, are going to be more aerobic in nature. So we use our aerobic energy system to produce energy for activities that last a long period of time. So again, comparing our aerobic energy system to alactic, okay, our aerobic energy system is used for long periods of time, but that aerobic energy system cannot produce a maximal amount of force. Unlike the alactic energy system, which can produce a lot of force, but only can produce that for a short period of time. So activities that mainly rely on the aerobic energy system are things like marathon runners, triathletes, okay, long distance swimmers. Those would be examples of different activities that mainly rely on the aerobic energy system. And finally, in between there, we've got the anaerobic lactic energy system. Okay. And these are mainly focused on different activities that last between 60 to 90 seconds. Okay. Good examples of these types of activities would be someone performing let's say a hockey player. Oftentimes a hockey player's shift there on the ice there could last like maybe 45 seconds, but sometimes even up to 1 minute and 30 seconds. Other examples would be running distance, sprint distances that are between 400 to 800 meters, okay, roughly there. So what's important about this here is that the anaerobic lactic energy system can produce more force than the aerobic energy system, and it can produce more force for a relatively longer period of time than the alactic energy system. However, that anaerobic lactic energy system does not last as long as our aerobic energy system, okay, nor can it produce as much force as the alactic energy system. So essentially, it's kind of like the better of both worlds. But it's not as efficient as the alactic energy system for producing force, but it's not as efficient as the aerobic energy system for being able to create force for a long period of time. Now, lastly, one thing I want to emphasize here is no matter the activity that you are performing, okay, you will always use all three of your different energy systems. So let's say I perform a vertical jump. The primary energy system I'm using is the alactic energy system to perform that vertical jump. However, my anaerobic lactic energy system and my aerobic energy system are still creating energy to be used in that vertical jump. However, the amount of energy that it's using is very small compared to the amount of energy that my alactic energy system is being used to perform that vertical jump. Likewise, if I'm a marathon runner and I've been running for a couple hours, am I still using my alactic and aerobic lactic energy systems? I absolutely am. However, the vast majority of my energy is coming from my aerobic energy system, and very little is coming from my alactic and anaerobic lactic energy systems. Here's an example of running various different distances there, their different durations, and the amount of percentage of energy system requirement needed to be successful in these different activities. So let's say I'm running a 200-meter dash, and let's say I can run it as fast as I can in 22 seconds. The anaerobic energy system is going to provide 71% of the necessary energy, versus the aerobic energy system is going to give 29% of the necessary energy. Notice though, as the duration increases over longer and longer distances, the aerobic energy system produces more of the energy, and the anaerobic system produces less of the energy. Okay. So as the duration increases, if we're trying to work out at as fast as we can for that specific duration, okay, the longer the duration goes, okay, the more the aerobic energy system is going to produce more of the energy, and the relatively less amount the anaerobic energy system produces. However, as we talked about previously on one of the other slides, the anaerobic energy system doesn't go away. It's still producing energy even at long distances. And likewise, even at shorter distances, the aerobic energy system is still providing some of that energy to be successful in that event. So depending on the sport you do and what the physical demands of that sport are, there's a different balance of aerobic to anaerobic energy production depending on what that sport requires. Here are a few different examples. A shot putter. Again, you can throw that shot once, followed by a long amount of rest time. Therefore, it's going to be produce the majority of its energy from anaerobic sources and minimally from aerobic. A marathon runner there, majority aerobic energy system and a minimal amount from its anaerobic energy systems. In soccer, because soccer involves sprints, followed by some jogging, followed by some walking, followed by sprinting, it's a combination of anaerobic and aerobic energy systems. So here's an example of how much each of the energy systems were used across a soccer match. 2009 study, watched 400 players in different game scenarios there. And here are a few different highlights from that study. First, 18% of the total distance covered was covered at high speeds. Okay? So let's say a soccer player covered 5,000 meters there across the entire match. Okay? Almost 1,000 of those meters there were covered at high speeds. So not jogging speeds, not walking speeds, but at high speeds. However, 70% of the total match duration, was performed, or the athlete was either jogging at low intensities or was walking. So even though soccer is a very explosive sport in nature, 70% of the total match there involved walking or jogging activities. The ratio of high to low intensity work there, meaning like sprints compared to walking or slow jogs, equated to 2 to 4 second sprint performed every 90 seconds. So again, that soccer athlete there was walking or slow jog for long periods of time, but then there was a 2 to 4 second sprint happening every minute and a half there where they'd have to go all out to try to perform a specific soccer action. Now, even though that's a very short amount of time, compared to at high intensities compared to low intensities, the amount of energy required to perform these short bouts of high intense activities, the total amount of anaerobic energy expenditure was between 11 to 27% of the total amount of energy used. So what that means there is that when that athlete was walking or jogging slowly, not a whole lot of energy was being burned. However, during those 2 to 4 second sprints there, a ton of energy, relatively 11 to 27% of energy was being used to perform those high speed sprints there, or fast approaches to the ball. So when we talk about muscles, we've been talking about different energy systems. Let's kind of shift our focus there to different biomechanical terms. And depending on courses you've taken in high school or college, some of these terms might be familiar to you. We're going to focus on 3 different laws for Newton there. First one being Newton's law of inertia, second one being the law of acceleration, and third one being the law of action-reaction. First of all, that law of inertia, or Newton's first law. What this law means is that an object is going to stay still if it's staying still, or an object that's moving will continue moving in the same direction at the same speed, unless some sort of outside force acts upon it there. So here's an example of this. If I'm sprinting there, my sprinting speed there, will change if I'm sprinting into a headwind, versus I'm sprinting into no wind. By that headwind coming at me there, it's going to force me to slow down. I'm going to try to speed up there, but that speed coming at me is going to slow me down. Another example, this might be sprinting straight ahead, and then the wind is coming at me to the side. So by it at my side there, it's going to try to force me moving side to side instead of me trying to sprint straight ahead. Another example of this might be a golf ball there. That golf ball is going to remain on the ground and stay at rest until an outside force, me swinging my golf club and hitting it, acts upon it there to move it from a state of rest to a state of moving. And the second law is the law of acceleration, okay? Meaning that how fast the object accelerates, okay, is proportional, or meaning it relies heavily on the amount of force acting upon it, okay? So essentially there, the greater the force, the greater the acceleration. Here's an example of the formula if you wanted to calculate force dependent on the mass of the object and its acceleration there. So for example, here we've got this weightlifter there. What this weightlifter is trying to do is lift the bar from his knees up to his shoulders there. In order to do that there, he's got to produce a ton of force to accelerate this bar from staying still at his knees to moving up, and so he can catch it there at his shoulders. Okay. In order to do that there, in order to create more acceleration, that this athlete here has to produce more force, okay, and act it on that barbell there so he can catch it. Third example there would be the law of action-reaction. Okay. What this means is that for every action there, there's an equal and opposite reaction that is occurring. Okay. So for example, let's take a look at a high jumper. Okay. A high jumper has to launch his or her body off the ground. Okay. In order to launch his or her body off the ground, that jumper needs to produce force into the ground, okay, by stepping down to jump. So as the high jumper is stepping down to the ground to jump, the ground is actually going to push force in the exact opposite direction of that foot going into the ground. And by doing that there, that allows the high jumper to launch his or herself into the air so that he or she can get over the bar. Okay. So again, law of action, reaction. For every action, in this case here, pushing force into the ground, there's an equal and opposite reaction, which is that high jumper launching him or herself off the ground. Next up, okay, let's talk about different types of motion. Okay. First of all is going to be linear motion. Linear meaning the line there, means essentially motion happening in a generally straight line. So if you think about a 100-meter dash, people are sprinting straight ahead because they're sprinting in one line there. Okay, that would be considered to be linear motion. Rotary motion, okay, means motion that it is rotating or going around some sort of axis of rotation. Example, this might be a high jump. Think of the high jump and the axis of rotation being the bar. Okay, so as that person launches his or herself over the bar, okay, that creates a rotation in his or her body to get around that bar. Okay? So rotary motion meaning that there's some sort of rotation around some sort of axis in the movement. Now, a lot of times in our activities, they require both linear and rotary motions occurring at the same time. Example of that would be, again, sprinting. So as this person's sprinting, he's sprinting straight ahead. Okay, so sprinting straight ahead is the linear motion. However, as a person's sprinting, this knee is going to extend, okay, and then collapse. Extend, collapse, extend, collapse. Likewise, same thing happens at the elbow. Elbow extends, collapses, extends, collapses. So there's rotary motion occurring at the elbows and the knees during sprint, but the athlete's also running in a straight line as well. So again, while activities can be generally categorized as linear motion or rotary motion, oftentimes the activities emphasize one or the other. So we talked about different motions there. How fast are those movements occurring? Okay. How fast they are occurring is determined by velocity. Okay. And the specific definition of velocity is going to be the displacement a body travels in a specific direction divided by time, or velocity equals displacement divided by time. Now, I'm not going to go into the nitty-gritty details, but displacement, you can kind of think about it as distance. Okay. Now, technically, displacement and distance are not the same, but that's for another topic for another time. So if you want to think about displacement as distance, that can work in our given situation here. So for example here, okay, if I wanted to find the velocity of someone in a sprint there, sprinting 100 meters in 10 seconds, I would take the displacement of 100 meters and divide that by the amount of time it took to travel 100 meters. So 100 divided by 10 equals 10 meters per second. So 10 meters per second would be that person's average velocity for this given activity. Now, acceleration means that velocity is changing, okay, in the positive direction, okay, meaning that velocity essentially is becoming a larger number. A good example of this would be speeding up. So the first few steps in a race there, your body is speeding up, and that would be a good example of acceleration. Deceleration is going to be a negative rate of change of velocity, essentially meaning slowing down. So as a person finishes a race and is slowing down there from their race, okay, that would be considered to be deceleration. Force, we've talked about force a little bit earlier on in this PowerPoint slide set. Okay, so let's talk about force a little bit more in detail. Force is some sort of push or a pull there, and that changes the state of motion of a body. Okay, meaning that that person or force is used to either help speed things up, slow things down there. Okay, or it might hold something in a place. Okay? So, for example, there. Person accelerating out of the blocks there, okay, needs to produce force there to accelerate out. Another example is decelerating by stopping a body that is moving. So in a javelin throw, person runs up, stops their body, and then launches the javelin in the air. So by having to stop the body, force needs to be used to produced there to stop the person from sprinting forward. Center of mass there is a term as where's the most central part of that person's body there, okay, depending on the person's position and how much matter makes up each of these different parts of the person. Essentially, think about it as the balancing point for the body. Now, what's important to note here is your center of mass can change depending on your arm and leg position there. Therefore, it is not a fixed point in the human body. It can change. Here's an example here. Okay, so oftentimes if a person's standing in place there with their arms at their sides, the center of mass there would be roughly around that person's belly button. Okay. However, in this case here, as this person's jumping in the air, the center of mass of this person is actually about where this arrow is pointing. Notice this center of mass is actually outside of the person's body. So essentially, just understand here that center of mass, that midpoint there between all different parts of that body, might actually lie outside of the actual person's body. Okay. But essentially where this point is, there's an equal amount of mass on all sides there as this person is jumping. Impulse essentially is taking force and multiplying it by time. Okay. Now understand here, with impulse, the change in velocity is dependent upon how much force is being produced and how long a time that force is being produced and being applied. Okay. So if we either increase the amount of force being produced or we increase the amount of time that force is able to be produced, we'll increase its impulse there. So the more time we have to produce force, okay, that will create more impulse. Or if we create more force in the same amount of time, that also will increase impulse. Example of this might be a person, again, accelerating out of the blocks. As that person's accelerating out of the blocks there, person's pushing down with a ton of force down and back. And the amount of time this foot spends on the ground would be the total amount of time that person's able to produce that force. So how much time that foot spends on the ground, multiplying by the amount of force being produced, we consider that person's impulse with this particular step. Now, when an object or a person launches him or herself in the air, okay, or that object travels in the air, okay, The path of the center of mass, or the center of gravity in the air, okay, follows what's considered a parabolic curve, okay, otherwise known as a parabola. So roughly, okay, where my pointer's at right now, this is roughly the center of mass there, or center of gravity for this particular long jumper. Okay, so as he launches himself in the air, this dot here will follow this arcing path in the air. Okay, so this arcing path moving to the side there, that's going to be considered the parabolic curve, or the path of the center of gravity is traveling when that body launches himself into the air. Okay. Now, a hinged movement is when the linear motion of an object is interrupted at one end of the object, but the other end continues ahead at an increased speed. Okay, so for example here, okay, this person, javelin runner, is going to run down the runway, okay, but then that runner is going to stop to throw the object. Okay, so person's stopping his or her body and then launching the javelin after that. Okay, so linear motion there is stopped at the person's body, okay, but the linear motion at the other end, okay, where this person's hand at, is going to increase faster as he throws the javelin. This in turn there will help throw that javelin farther. So when we're applying force, okay, whether it be sprinting or we're trying to hit a certain object, that force should be produced in a specific direction depending on the activity that we want to, what we want to accomplish. So this person hitting this ball here is producing force in a horizontal direction. Some people might want to produce force there in a vertical direction, such as you're trying to take a medicine ball and toss it above your head as high as you can. Other times you might want to produce force in a downward direction. For example, if someone's dribbling a basketball, you want to produce a force downwards to push that ball into the ground. So the direction of force depends on what type of outcome we want in the given activity. So when we produce force there, okay, it's not just force at one area of the body. There's a summation of forces, okay? So forces coming from several parts of the body, okay, and adding up together, okay, to create the intended outcome. So let's take a look at this example of this shot put thrower there. Okay? Shot put thrower typically produces forces there using the bigger muscles towards the center of his body, towards that center of gravity, essentially. So the muscles of the hips and the legs and maybe the torso. Then as that person spins and throws, okay, he's going to finish with producing forces in the muscles towards his extremities, those muscles in his wrist and in his fingers there. Okay? So more force is being created with the bigger muscles at the beginning to get the force going, and is going to finish with forces produced with the smaller muscles towards the ends of the person's body. So essentially you add up the forces of being produced towards the middle of his body and the forces used towards the end of the body, and all those forces together there and the different directions they are being applied will end up with the result of the distance that shot put is actually thrown. That's all I got. If you have any questions, let me know. Have a good day. Booyah!